Okay, great. And well, thank you for the introduction, and thanks also to the organizers for the invitation, and to Demi in particular. Okay, so okay, so I just want to talk a little bit about some recent work I've done on the control theory for wave equations, and also talk about some of the methods used for establishing these fairly new results. And so as a bit of an outline, so kind of what I want to do for the first part of the talk is to give a bit of a survey on what's been done for controllability of wave equations. I'm not sure of how many people in the audience are familiar with the problem and with the background, but here hopefully it can kind of give something that everybody can take with them. Okay, and then after that, I want to talk a bit about the main results, which is with the same problem, control of wave equations, but now on domains that change with time. And so I want to mention the new estimates that will go toward proving these new results. And then with whatever time is remaining, I want to talk about some of the ideas that prove, right? Mainly these Carleman and these observability estimates that go into this. And I also want to connect these ideas with ideas from Lorentzian geometry and also relativity, right? And also some ideas from conformal geometry. Okay, so that's the basic plan for the talk, and we'll just see how this goes. Okay, so let me first begin with something very, very basic, which is just a classical wave equation, right? So here by this box, I just mean the usual wave operator in, say, n+1 dimensions. And so this box just means, I guess, it's a bit of convention here that we take this box to be minus dt squared, and then plus the Laplacian in the spatial variables. I just write this down on the board on the right hand side, just in case people forget about 15 slides later. Okay, but now what we're mainly interested in are more general class of wave operators. So this is these linear operators that involve this box, but then plus lower order terms, right? So here we have this L, which is not just the wave operator, but also plus a first order term. So this X is a space-time vector field that represents the coefficients of the first order terms. And then you have some potential V as well. Okay? And so here, both V and X will depend very generally on both the spatial variables X and on the time variables T. Okay, and then here we're also concerned with solving the wave equations on bounded domains, right? So for this first part of the talk, we will let omega be this open bounded subset of Rn, and just to keep things relatively simple, we say that omega has a smooth boundary as well. And here we're also concerned with a finite time interval. So this is the initial time, which are called t minus, and then the final time, which are called t plus. Okay. And so then the general wave equation we're going to be looking at is of the form, say, L of phi is equal to f. So L is as above, and then f is some forcing term. And this is on t minus t plus across omega. Okay, so then for anybody who's seen a bit of PDEs, you know that one has a unique solution of this wave type equation as long as you're given some initial data. So this is phi and also its first time derivative at the initial time t minus, along with some boundary data, right? So this is usually, in most cases, either the Dirichlet data, so this is the value of phi itself on the boundary, or the Neumann data, which is the value of the outward normal derivative of phi on the boundary. Right, so this is very, very well known, so I don't need to say more about this. But now the main question here is something that's a bit more, say, proactive, which is that, well, can we control what happens to the solution phi, right? So for example, given some initial state, say phi dt phi at some initial time, say t minus, then can we achieve any final state that we want at some later time t plus. Okay, so that's the basic question. And of course, we want the way that we approach this question to at least somewhat reflect what's happening in the real world. And so in the real world, we can't just kind of tell our solution to just become like this, right? We can only directly affect part of the system. And that's what we call the control. Okay. So in particular, on the mathematical side, this is usually done in two different ways, right? So one can impose a control either through a forcing term in the equation. So here we instead look at, say, L of phi is equal to some forcing term G, and we can also stipulate that this forcing term is only supported on some subset of your spatial domain. So this little omega. Okay. And one other way of imposing control is through the boundary data, right? So here we look instead at the homogeneous equation, so L phi is equal to 0, and we pick some subset gamma of the side boundary. And then what we want to do is we want to basically steer the system using either Dirichlet data on this subset gamma or via Neumann data on the same subset. Okay. And so here, to keep things relatively simple, let's focus only on the Dirichlet boundary control problem. So other problems can be approached in similar ways. So I just want to focus on the Dirichlet side of things. Okay, so now with that in mind, one can give a more precise statement of the controllability question. So here we're again given the control region. So this is again a subset gamma of the side boundary. So this is again the region of the boundary where we're allowed to impose our boundary control. Okay. And so the question is given, say, any pair of initial and final data. So this is phi 0, phi 1 plus and minus. This represents the initial data for minus and the final data for plus. Right? The goal now is to find some control or some boundary data, say phi sub d, that is supported on the subset gamma, such that if you solve the initial boundary value problem with the initial data at phi 0 minus phi 1 minus, and then with the boundary data phi d, right, then you achieve the final state, phi 0 plus phi 1 plus that you want. Okay, and this is if that's a bit much, then this is kind of shown in the picture on the right, So this red part and the green part is kind of well, okay. So you want to start from the red part and you want to get to the blue part, and you can basically choose whatever green part you want to get you there, right? And so the simple way to state this in one sentence is whether solutions can be controlled via your given Dirichlet boundary data.
And will it depend on the properties of the billiard with the boundary of your domain? So I'm just some of my intuition comes from classical mechanics, and then if you have a cross section, if you have ergodic billiard, then sort of every trajectory visits the boundary, and then you can sort of hope to control. Is this intuition more or less reasonable, or it's not quite what?
Well, it's actually exactly the intuition in the case when your equation is time independent or time analytic.
Okay.
Yes. Right there, there's a lot of microlocal based results. That's exactly based on this.
Okay. Thanks. Sorry for interrupting.
Yeah, no problem. It's good to know that I'm not talking to nobody. So. Okay, but we'll get there soon. Right, so a couple of basic observations from this problem. The first one is that one can, without any loss of generality, take either the final data or the initial data to be 0. Right? And this is what's commonly called the problem of null controllability. Right, and one can do this because one can always subtract a solution or any solution of the wave equation with 0 boundary data. Right? You get an equivalent problem. Okay, and so then for the next few slides, we'll just assume that that the initial data will be 0, and we can ask if we can achieve any possible final data through the boundary data. Okay. And the second The second main observation is something special to wave equations, and this is the notion of finite speed of propagation. Right? And this is this property that if you put information on the boundary, then it needs a certain amount of time to travel to all of the interior. Right? And so this essentially puts a fundamental lower bound on the amount of time you need to impose the control before you can control your entire system. Okay, so with that in mind, let me say a few words over the next 2 slides about how this problem is usually solved. This is not the most modern method, but perhaps this is the most elementary way of looking at this, right? And so here the idea is that we let this S be this linear operator, right? And so what this does is as follows, right? So basically what you're feeding into this operator S is some Dirichlet boundary data. And then what you do is that you solve your wave equation L phi is equal to 0 with 0 initial data, and then this given boundary data phi d. And then what S gives you in the end is just the state of your system at the final time t plus. Okay, and so since our goal in exact controllability is to show that we can get to every possible state, right, then the goal here is to show that this operator S has full range. And one technical point is that here we're taking our states to be an L2 cross H minus 1, and there is a way to make sense of these solutions. Right? This goes back to the ohms and many others, right? But I won't get into that here. Okay, oops. Sorry. Okay, and okay, so then the main idea here is that we want to look at the adjoint of this operator S, and so here S star, we want to see what this S star does, right? And so if you kind of do the elementary computations, you can see that what this does is that what you're doing is you're feeding into this S star basically the final state of a system, right? So this C1 plus, C0 plus, okay? And then what you're doing with it is that you're solving the adjoint equation, which is again still a wave equation, and you're solving it backwards in time. And now with 0 Dirichlet data, and then what S star spits back out at you is a Neumann data on the boundary, right? On the subset gamma of the boundary. Okay, so then the main idea here is that if you apply a bit of functional analysis, then well, this controllability problem is which is equivalent to showing that S is surjective. Then this is by duality in the closed range theorem, just equivalent to S star being injective and also having this linear bound, right? And so now if you keep in mind what this S star is and you write out this linear bound, then what you get is what is known as the observability inequality. Okay, so let me just write that. Down here, just as something that is a fairly important, and again here we're solving a problem with 0 boundary data. Okay, and okay, and so then basically in this whole control machinery, the main goal is usually to prove this observability inequality, right? Because by various functional analysis machinery, this is exactly equivalent to the control problem that we discussed earlier. Okay, so this becomes the goal. Okay, and with any discussion of this observability controllability, I have to mention Lyons, who came up with what is now called the Hilbert uniqueness method, right? And this is essentially the modern machinery for kind of navigating this observability and controllability thing. And it's a bit more powerful than what I mentioned in the sense that one can also kind of using this machinery generate the optimal control that minimizes here the L2 norm on the boundary, right? And we can generate this as a minimizer of some functional as well. Okay, so let me also mention some of the common methods that people have used to prove observability, right? So I think the earliest methods people have done are via Fourier series, right? And so this is usually applied to wave equations in one spatial dimension. And so this is, the main idea here is to apply refinements of what's called Ingham's inequality, right? And so this is I just gave this below, right? This is just the statement that as long as you have a certain gap between various eigenvalues here, then of your Schrodinger operator, right? Then you can separate all the frequencies given enough time, right? And one can essentially apply something like this directly to the wave equation to prove observability. Okay, but we won't be getting into that this talk. So let me just not say any more about that. Okay. The second method is what's called the multiplier method, and now this is something that's directly applicable to all spatial dimensions, but it's usually only applied to the free wave equation, right? So where L is just the box itself and X and V are 0. Okay. Okay, and so the main idea here is is just to start with the integral over your space-time region of box of psi times S star of psi. Right, and so since box of psi is 0, then this whole thing is 0, right? And then you want to take this and you want to integrate by parts, and then eventually, after integrating by parts and doing some conservation of energy, then you get the result that you want. Okay, but kind of what I want to mention here is the results that you get, right? And here this is given in the theorem below, right? So you fix some center point in space x0. And then you make this assumption of, on the time span t plus minus t minus, right? And basically that it has this minimum here, or that's bigger than this minimum value. Right? And so one way to interpret this 2-time soup that you see on the right-hand side is that this represents the amount of time that you need for information on the boundary to travel to this point x0, and then to travel back to the boundary. Right? That's how one should read that. Okay, but now if you have this lower bound on the time span, then for the free wave equation, one has the observability estimate that you want now with a certain gamma. Right? So let me again just take a few extra seconds to write this down, just because I think we'll end up comparing to this region when we state our main results. Okay, so this gamma is just a set of all points on the boundary satisfying that this inequality here, this dot product with the unit normal is bigger than 0. Right? So here this nu is just the outward pointing unit normal on the boundary of omega. Okay. And so the way to interpret this condition that defines this gamma is as follows, right? So if you take a point, say x, on the boundary, then you just draw the ray from x0 to x, and then basically you're in gamma as long as this ray is at that point leaving the region, and you're not in gamma if you're entering the region at that point. Right? This is very crudely demonstrated in the picture on the right, on the bottom right here. Okay, so the next family of methods are what are known as Carleman estimates, right? And so these are weighted space-time integral estimates with a free real parameter, right? And the contribution of these methods is to extend what we were able to do with multiplying methods to general operators L with low order coefficients, right? And so these Carleman estimates, they look something like what's in the middle of the slide. So on the left, you have this control over the H1 norm of psi with some weight, and then on the right, you have a box of psi, and then this factor lambda to -2, right? And then plus maybe some boundary terms on the right, depending on how you want to use the estimates, right? And so what's new here are these is this weight e to the lambda f, right? Where f is something that's very specially chosen, and then lambda is this free real parameter that's large. Okay, so now the idea here is that since L is now box plus lower order terms, right? So then on the right, when you look at box of C, you're going to get something lower order. You're going to pick up an H1 norm. Right, but on the other hand, because you have this large lambda and this now very small factor lambda to the -2, then you can take kind of these factors on the right-hand side and absorb them into the left. Right? And this is how Carleman estimates can help you deal with lower order terms in your wave equation. Okay, and so the results that come out of these Carleman methods that began in the mid-90s, right, is that the previous theorem that I mentioned for the multiplier estimates also hold for general operators L. But on the other hand, there is kind of a somewhat stupid technical thing, which is that kind of all these Carleman results, you also require that this point x0, which determines your control region, it has to lie outside your spatial region. Okay. And I'll come back to this point later on because that's something that we'll remove in our main results. Okay, and then finally, the last kind of family of results rely on microlocal methods. And so these are essentially the most precise and also the most optimal results, at least with respect to the region where you impose your control, right? But on the other hand, the price you pay for that is that you have to assume that X and V here are time independent, or at the very least time analytic. Okay. And so the results, the similar result here is due to Bartos, Lebeau, and Rausch, and this is from the early to mid 90s, right? And so this says that you have observability on the subset gamma, and this is equivalent to what's called the geometric control condition, right? And so this is just the statement that if you look at every bicharacteristic or null geodesic, if you're more geometrically inclined in this region, then it has to hit this boundary part gamma. Right? And the idea is that in high frequencies, right, all the information propagates along these bicharacteristics, right? And so you have to make sure that these hit the part of the boundary that you care about. And also here we have to also stipulate that these bicharacteristics that they reflect off the boundary via geometric optics laws. Okay, and then there's also been some recent results over the past 5 years or so that also extend this result to subsets of the boundary that are time dependent, right? Not just t minus t plus cross something spatial. Okay, and just to summarize a little bit here on the Carleman and microlocal methods, right? So as I just mentioned, these microlocal methods give you stronger results in the sense that they give you kind of the best possible control regions, gamma, right? Whereas on the other hand, for Carleman estimate methods, then they give you more robust results in the sense that you can handle a larger family of PDEs, right? And in particular, we can look at coefficients V and X that are only smooth, or even C2 or C1, right? Rather than time analytic. Okay. But on the other hand, in higher dimensions, one cannot achieve this optimal geometric control condition via Carleman methods. Right? So that's the drawback there. Okay. But for the current talk, our main interests are in the robustness side of things, right? So we're interested in equations where V and X may not be analytic, right? And this is well, for this talk, it's mainly due to the fact that we're looking at time-dependent domains, but also for the future, it's also because we want to look at methods that extend to nonlinear wave equations. So we want to kind of look at things that could apply there, right? Hence, we don't want to assume any kind of analyticity. Okay, so the next part of the talk is now on the main results of the paper. But before I go on, let me ask if there are any questions so far.
And have people looked at dynamics of domains whose boundaries depend on time?
Yeah, I have. I'm not the only one, but yes.
I see, I see. Yeah, okay, because I guess there are some sort of classical dynamics could be interesting. Okay, I haven't seen such things, but it's
it's pretty rare. I think that's kind of one thing that we do in this result, right? Is to look at these domains that also change in time.
Because you can sort of have you know, some your domain, starting off, your domain is boundary curve, let's say in the plane is not flat, you know, positively curved. Then you have integrability or KM type, and then you get some flat piece, and that kind of changes stuff. So you can have some sort of your boundary go through a phase change of what kind of dynamics you're going to have. So that could be interesting in the neighborhood of that. But maybe it's not so well for controllability. I don't know. Classically, if you think about dynamics, that could be fun.
I see. Yeah. I mean, I guess in this talk, I certainly talk about boundaries that change in time. I don't know if I quite do what you're talking about, where you actually have some kind of a serious topological change.
Yeah. No, I'm just thinking out loud. Sorry.
No problem. Okay. Any other questions? Okay, so then let me move on to the next part, which is to discuss the main results, right? And so now we want to take everything we've talked about before, but now let's ask, well, what if we look at time-dependent domains, right? And so here, essentially, it's the same as before, except now the spatial domain omega also depends on your time variable, right? And so we'll call this time domain U. Okay. So I guess the picture is again something that changes in time, and we'll call the interior part U, and we'll call the boundary, I guess, UB. Right? This is just the union of all the boundaries of the omega times T. Okay, and so the only kind of the only fundamental assumption we make here is that the side boundary U sub B is time-like, right? And that's terminology coming from relativity, but on the analysis side, this just means that this boundary moves at less than the wave or characteristic speed, right? Or in practice, this means that the boundary is appropriate for putting boundary data for the wave equation. Okay, and so in this kind of a dynamical moving boundaries domain, one can still get the same kind of well-posedness results for the wave equation. So one can still, again, uniquely solve this wave equation L of E is equal to 0, given initial data at some fixed time t minus, and say Dirichlet boundary data here on U sub B. And so because of this, we can again pose the analogous control problem, which is that well, given some subset, we'll call this Y of the boundary U sub B, then what we want to show is that for any pair of initial and final data, so initial and final states at say some time t minus and t plus, then you want to find some Dirichlet boundary data phi d supported only on this subset Y that takes you from the initial state to the final state. Okay, and long story short, one can again run this Hilbert uniqueness method of machinery that I discussed earlier, and one can show that this exact controllability problem is equivalent to an observability estimate for the adjoint system, which here again looks the same as the one that I wrote before. Right, you want to control the energy of your solution with zero Dirichlet data by the Neumann data on this subset of the boundary, right? Or this is a statement that you can observe the entire solution over this period of time from just the Neumann data. Okay, so the people have looked at this problem with moving boundaries, but not too many, right? So there's only a very sparse collection of results, right? And so first of all, for general spatial dimensions, right? People have really only looked at this for the free wave equation, and so one of the main results come from Bardo and Chen in the mid 80s, right? And so this only applies to the case where U is expanding, right? And so there you have extra decay for your wave equation, and you can use various stabilization methods. Then there's another result from the mid 90s from Miranda. And so this covers the case when U is self-similar. So it's every time your spatial domain is a rescaling of that from initial time, and then also asymptotically as t goes to plus or minus infinity, your domain becomes asymptotically cylindrical or static. And then more recently, in the past 7-8 years or so, right, there's been a number of results, again, for the free wave equations in one spatial dimension, right? And so there's been various results covering the case where the boundary is given by 2 lines. So usually one vertical line and one slanted line, right? And so there they have optimal results in terms of the control region. And then that's been generalized to where U sub b is a line plus some time-like curve, right? And there I'm not sure if they have the optimal results yet. Okay, but what's missing from this picture are general results in any dimension. And now with that in mind, I can give a rough statement of the main results of this talk, which is essentially a general result for the previous problem in all dimensions, right? And so let me just quickly go through this statement, right? So the theorem says that, well, let's consider, again, a general wave operator on this moving domain U, and we again fix some center point x0 in space, and we assume this lower bound on the time span, t plus minus t minus, right? And this is exactly analogous to what we showed earlier in for the multiplying method, right? So you want to give yourself enough time for the information from the boundary at time t minus to go all the way to the point x0, and then back to the boundary at time t plus, right? That's essentially what this lower bound says. Okay, so then under this lower bound on the time span, we have then our desired observability estimate for the adjoint problem, right? Which is the same as before. And then moreover, this observation region, which translates to the control region, this y, is much smaller and a time-dependent subset of what you would get from your previous multiplier and Carleman methods. Okay, and I'll say more about kind of how that's smaller as we talk a bit more about the proof. Okay. And then, of course, the main corollary of this is that one then achieves exact controllability for the original equation L with the same control region Y. Okay, a couple of quick remarks just to compare to previous results, right? So this particular theorem that we have here, this is actually enough to recover all the existing results in one spatial dimension. In particular, this applies to a general region there where both boundaries are given by time-like curves, and it also recovers the optimal time span that's dictated by the geometric control condition, right, for any such region. Okay, now similarly in higher dimensions, this is, as far as I know, is the first result for general time for general regions in higher dimensions with moving boundaries and for wave equations that are not that contain lower order terms. Okay. And moreover, if you apply these results to back to the previous case where the domain is static, then you actually get an improvement over the previous Carleman or multiplier results, in the sense that you achieve a smaller control or observation region, Y. Okay. And then I mentioned this technical issue that in the Carleman estimates, this X naught can only be outside the domain. But here we also have a way of establishing results even when X naught is inside the domain. But again, because these are based on Carleman estimate methods, then it does not, at least in higher dimensions, achieve this optimal geometric control condition that you get from microlocal methods, which actually don't apply here.
And do you know, kind of an, again, a little bit to the side, suppose you don't, maybe not the boundary changes, but the elliptic operator changes, the main symbol. With time, maybe also slowly somehow. Can one, I suppose one can also ask whether you can, suppose you know how changes can one also control. Is it interesting, and have people thought about this?
I'm thinking about it now, actually, with one of my
okay.
That's the next goal as well.
I see. Yeah, no, but it looks like a reasonable question. So you can change various things, like you change the boundary, and then you can also change the symbol. Yeah.
Of course. Yeah. No,
okay.
I think that's something that hasn't been explored much in the literature. I mean, I think people who work in control are generally not Lorentzian geometers. Right? So people have studied. People have studied very much the wave equation on a fixed Riemannian manifold. Right. That's been done quite a bit.
Yeah. No, but yeah. Okay. Thanks. No, but it's good that because the question seems reasonable.
Yeah, absolutely.
Thanks.
Okay, so anyways, that's the the statements of the that I want to prove in the remainder of this talk, right? And so let me here now give a quick outline for how I want to approach the last bit of the talk. Right. So okay. So first of all, I want to basically talk about how I'm able to achieve the result for domains that are time dependent. And so here we want to look at a simpler model problem, which is just the free wave equation. And what that allows us to do is that allows us to actually apply just purely multiplier methods, right? And so we can avoid all the complications from Carleman methods and just look at the ideas that let us achieve these time dependent domains. And then for the second part, I want to now go back to general wave operators with lower order terms, and then say a bit about how one proves these Carleman estimates. And then for the last part, if there's any time, I'll say just a little bit about how one goes from Carleman estimates to the observability estimates. It's mostly a standard process, but there's one thing new, which is this technical point of achieving this X naught being inside the domain. Okay, but okay, we'll see how time goes. I think I'm a bit behind anyway. Okay, now for the first part, let's now go back to the free waves, right? So to kind of explain how we achieve moving. How we take care of these domains with moving boundaries, we have to first say a little bit more about how the classical multiplier result works. Right? So I mentioned several slides ago that the starting point of this method is to we'll start with 0 is equal to the integral over this space-time region of box psi times some multiplier applied to psi. And I can even tell you what the multiplier is. It's just I guess RDR of psi, right, plus a constant times psi. That's essentially what that is, right? And so now if you do the integration by parts and you apply conservation of energy, then and you do it correctly, then what you get at the end of the day is this inequality in the middle of this slide, right? And so here this script E is just the energy of the wave equation, and so you have this on the left-hand side, this t plus minus t minus, this time span times the energy, and then on the right, it's 2r, where r is as we defined before. Right? And then you have a boundary term on the right-hand side as well. And so the main point is that if you look at the things in green, right, then as long as your time span t plus minus t minus is bigger than 2r, then you can move that term from the right and absorb it into the left, and you see that the energy is precisely controlled by this boundary term. Now for the boundary term, the main kind of point comes from this part in orange, right? This dot product. right? So then as long as this part is negative, then that entire part of the integral is negative, and you're free to drop that. Right? And so the only point you have to keep is a portion whenever this dot product is positive, and that's exactly what gives us this region gamma that we mentioned before from the multiply methods. Okay, so that's a one-slide summary of how this works, right? So now, if you were to go from this to the time-dependent domains, then well, the main issues are as follows, right? The first one is that you no longer have conservation of energy. Right? This changing of the domains can add or take away energy from your system. And then the other part is that if you want to do integration by parts and energy estimates, then these will give you additional boundary terms that if you don't do correctly, can be quite messy. Okay. So now the way that we deal with this, there's just a couple of things we do. Right? The first one is that we want to replace this idea of this reference point x naught by a reference event, right? So we not only have a central point in space, but also a central time, t naught. And then kind of with that in mind, we want to kind of view everything in terms of the space-time or Minkowski, right? Rather than the spatial geometry. And so Minkowski space-time is just R1 plus n, with the metric is looking just like the Euclidean metric, but now with the sign of the time part reversed. Right? And so this is the geometry that one usually associates with the theory of special relativity. Okay, and it's a very useful geometry to have because the wave operator is very intrinsic to that geometry. That's where that comes from. Okay, and so then the second idea is that you want to take this multiplier S naught that we had before, and we want to add an extra term. Right? In particular, we add this extra term containing the time derivative to this. Okay, and so if you're used to a Minkowski geometry, then you can see that the principal part of this operator S star, then this corresponds to the gradient with respect to the Minkowski metric of this function f naught, right, which is whose level sets are hyperboloids. Okay, and on the more practical side, you can see that well. Okay, this new term that you add to the multiply, this gives you kind of I guess more terms in the integration by parts, and then this dt part actually corresponds exactly to the energy conservation arguments that you saw that one sees in the classical computations. And then the last idea is to well, do all the integration by parts with respect to the Lorentzian or the Minkowski geometry rather than the Euclidean geometry. Right, so you can somehow kind of take care of any changes over time in the domain, because it's in the same way as you would any kind of a curvature in the spatial domain. Right? It's by treating these geometrically. Right? And so the upshot of this is that whenever you get a unit normal on the boundary, what you get is the outer pointing Minkowski unit normal with respect to the Minkowski metric rather than the Euclidean metric, right? And so this is just the Euclidean normal, but with the time component reversed in sign. Okay, and so if you kind of take all these ideas together and you do a couple of pages of computation, then you get essentially the observability estimate that I mentioned in the main theorem, but now only for the free wave operator, right? So you have the same lower bound on the time span, and then you have this observability estimate, right? And so I guess the only kind of new thing here is I say a bit more about the observation region Y, right? And so Y is now, this is just the intersection of the boundary of the domain with a set of points satisfying the condition that this n applied to F0 is positive. And so here n is, as before, just this outer pointing Minkowski unit normal to the boundary, and then F0 is this hyperboloidal function that we had before. Okay. And I'll say a little bit more about kind of how one parses that condition. Okay. And then the center time is just this time is this t naught that's chosen to be in a way halfway between t minus and t plus in this sense. a couple of remarks. Well, the proof of this multiplier result is actually pretty embarrassingly easy. It's only about 2 pages of fairly simple computations, right? But it's enough already to achieve kind of this control for the moving domains, right? In particular, for one spatial dimension, it's enough to recover all the existing results and in the full generality, at least for the free wave equation. And then in higher dimensions, it's enough to handle general domains that can change in time, right? And it already requires a much smaller time span than before, right? Compared to existing results, and it's optimal in many ways as well. Okay, now for this condition, this n of f0 is bigger than 0, that characterizes the part of the boundary where we have to impose our control. Then one can view this as a generalization of this condition that we had for the classical multiply method, right? So in particular, if you take the special case where our domain U is time independent, and you kind of compute and expand this condition, then this is exactly the same as the one that you get from the classical results, right? So that's one thing. And then okay, next, if you look at the case when U is expanding away from this center time T naught, then at those points where U is expanding, then one needs a slightly smaller control region Y. And then when U is contracting away from time T naught, at those points, one needs a slightly larger region. Right? This is a bit hand wavy, but roughly speaking, that's the way this works. Okay, so that's pretty much the story for the multiplier side of things, and also for how one achieves boundaries. But now let's go back to the question of how do we achieve a similar result for general wave operators with lower order terms. And so here the goal is to establish a global Carleman estimate that will let us accomplish this task, right? And so again, this Carleman estimate will have the following form. So you're again controlling some weighted H1 norm on a part of your spacetime domain. You're controlling this by a weighted L2 norm of box of Psi. And then on the right, I'm a bit more specific here, right? This is the boundary term that contains the Neumann data, essentially. Okay, so then, well, one can spend several hours deriving these Carleman estimates, but in half a slide, how does one try to do this, right? Then from the geometric point of view, one can think of this as a multiplier estimate for a conjugated wave operator. So if you take the wave operator conjugated with this weight e to the lambda f, right, and then you apply it to this to the unknown, but also renormalized with the same weight, right? Then this is the starting point of the Carleman estimate is essentially the starting point of the multiplier estimate for these conjugated quantities. Okay. And then from there you do a bunch of computations, and I won't get into that here. Okay, but let me say something about kind of how one constructs this Carleman weight, because it's one of the that's the main novel part about the proof of this Carleman estimate. Okay. So here to give the basic idea without kind of overcomplicating things, let me lie to you just a little bit, right? And say something that's almost true but not quite true, right? And that's the statement that this weight e to the lambda f is constructed from this function f naught, right? That whose level sets are these hyperboloids. Okay, this isn't quite true, but it's true enough to get most of the basic ideas, right? So let me just I guess go with that lie for now. Okay, and then actually I have to give the exact formula for e to the lambda f, but let me just leave that there. Okay, so then if you kind of look at what this f naught is, then these level sets of f are just hyperboloids, right? In particular, if you take f naught is equal to 0, then you get this null double cone that's centered about the vertex t naught x naught. And then if you look at f naught is equal to a positive constant, then these are the one-sheeted hyperboloids in the exterior of this cone. And in fact, that's kind of all we'll be concerned with. Right? So let's we'll call this D naught. This basically the set of all points where F naught is positive. So we're looking at the exterior of the null cone. And so all of our analysis will now be restricted to this exterior. Okay. And by the way, how much time do I have?
We started a little late, so well, maybe 7 minutes to 1 hour, but maybe take a few more minutes if you'd like.
Okay. Okay. So well, I just want to make sure I don't take too long, but sure. Just let me know if I'm overstepping too much. Okay, so we have this Carleman weight that's based on this function f0, right? And so the main feature here is that if you look at this e to the lambda f, which is this on the previous slide, this f0 to the large power lambda times this exponential that we don't particularly care about, right? Then if you look at this null cone, which is just f0 is equal to 0, then this weight vanishes. Okay, and so what this means is that if we were to kind of restrict our estimates to the exterior d0, right, and you do your various integrations by parts that you always do, right, then you don't pick up a boundary term on this cone, f0 is equal to 0. Okay. And so that's really have the main analysis idea here, right? So you can basically run the Carleman estimates on this domain on U intersection with this null cone exterior, and again you don't pick up boundary terms on the cone itself. You only pick up boundary terms on the side boundary, right? U sub b, and now intersection with the exterior d naught, and so you get something of this kind. Okay. And so now if you take this Carleman estimate and you apply to it energy estimates via some pretty standard processes, then what you pick up is essentially the observability estimates, but now with the observability / control region Y a bit smaller than before, right? So Y will be kind of what you had before, this U boundary intersection with this condition that n of f0 is bigger than 0 from the previous discussion. But you also restrict now to the exterior d0 of the null cone, right? And this is the main improvement in the observation region that I mentioned earlier, is that you again can restrict this region that you impose the control to the null cone exterior as well. Okay, and probably the better way to demonstrate this is through some pictures, right? So here on the left in orange is just the boundary of our space-time domain, which is changing in time. And now in the remaining pictures, basically this has red dot indicates the reference event, this T0 X0 that we have in our setup. Okay. And so then what's in purple, well, okay, actually let me just look at the second picture here, right? So here this T0 X0 is in the interior of our domain, right? And so then in this case, what our region Y will just be the full intersection of the null cone exterior with the boundary, right? And this is the part that's given in green. Okay. Now, in the right half, in these two pictures, we look at a separate case where the reference event T0 X0 is outside our domain, right? And so now this part in purple here, this is the full intersection of the boundary with the null cone exterior, right? But now only a part of this boundary will satisfy this condition that n of f0 is bigger than 0, and that's the part given in green, right? And so that's is our region Y, where we have to impose our controls according to our Carleman estimates here. Okay, I'm a bit low on time, so let me skip the relativity interpretation, but one can kind of think of this in terms of special relativity as well. Okay, but so a few slides ago, I mentioned that I lied to you slightly in the sense that in the statement that these Carleman weights are constructed from this function f0, right? And so the main point is that, well, if you're familiar with Carleman estimates and the underlying unique continuation theory, then you know that the main requirement for these estimates is a property for the weights known as pseudoconvexity. Right? And the bad news here is that the level sets of this hyperboloidal function f0, they barely fail to have the pseudoconvexity property. Right? And this comes from the fact that you have these bicharacteristics that rule these hyperboloids. Okay. But in practice, the upshot of this failure of pseudoconvexity is that if you use this weight that you generate from this f0, then one can only obtain this degenerate Carleman estimate, which looks very much like before, except that on the left-hand side, you can only control the L2 norm and not the full H1 norm. And so since for the observability estimate, we actually require bound for the full energy or for the H1 norm, then this is essentially not enough for the observability estimate and hence for the control results. Right? And so the upshot is that, well, we cannot use this function f0 to build our Carleman weight. Okay, and so the idea to overcome this is essentially to perturb this function f0 to some other function, say epsilon, such that these level sets are close to what we had, but they actually now have the pseudoconvexity property. Okay, so this idea of perturbing these functions, this is not new. This is this has been done in these classical in the classical results in the literature. And so what one usually does is one basically takes this function f0 and one multiplies this time part by something slightly less than 1. Right? And this essentially corresponds to hyperboloids for waves with a slightly slower speed. But now kind of this, if you look at this function, then its level sets will now be pseudoconvex with respect to our original wave operator. Right? And this is what people usually do. Now, the drawback of this approach is that this function f epsilon is no longer well adapted to the characteristics of the wave equation, right? And so, and the upshot of this is that well, one can no longer using these not well adapted functions obtain these Carleman estimates that are supported only on the null cone exterior, which was our main game here. And then also, there's also a drawback with this technical point, that is that this only works whenever your reference event is not in the region. But let me not mention that anymore here. Okay, so maybe in the final few minutes, I'll just talk about how we approach this perturbation instead. Right? This is the last main idea here. Right, and so well, what's different from I guess what's done in this result is that instead of perturbing this function f naught directly, we instead perturb the geometry. Right, and I can even be a bit more explicit here. Right, so let's take instead of the Minkowski metric, what I call the warped Minkowski metric. Okay, this is given by this g sub epsilon. So notice that if you take epsilon is equal to 0, then what you get is exactly just the Minkowski metric, but in spatial polar coordinates. Right, and so this is essentially you're just taking the Minkowski metric and you're adding a bit of a kick, an epsilon kick to the angular part of the metric. Okay. But kind of what's interesting here is that if you take this kind of slightly perturbed geometry and you look at the same function f0 as before, then this f0 now becomes pseudoconvex with respect to this slightly altered geometry. And now the second observation here is that if you look at the exterior with respect to the original Minkowski metric, and then the exterior with respect to this warped metric, then they're actually conformally related. Right? If you do the correct change of variables, you can see that this g epsilon is actually just a conformal factor times g, or the pullback of g. And so now, what's well known is that this pseudoconvexity property is in fact conformally invariant, right? And so then, because you have this conformally related geometry where with level sets of F naught are pseudoconvex, then you can construct a pseudoconvex foliation on your original Minkowski geometry by pulling back this F naught through this conformal isomorphism. Okay. And so what this leads to is the following strategy for proving the Carleman estimate, right? And so the first step is that you want to look at this warped geometry, G epsilon, where the level sets of this F naught that we mentioned before are pseudoconvex, and you want to prove a Carleman estimate in that setting, right, which is relatively simple. It's not a very complicated geometry. And then what you want to do is that you want to use this conformal relation to pull back this Carleman estimate on the warped geometry to an estimate on the original geometry, right? And that is essentially kind of how this is done. Okay, I think I'm quite low on time, so let me skip this part, this last part about getting the Carleman, getting the observability estimate from the Carleman estimate. And let me just finish by giving a more precise statement of the main observability estimate, right? So here we're now looking at general wave operators on a domain with moving boundary. Again, we make the same assumption on the time span as before, so there's not much to say there. And now we have observability for the adjoint problem that's given by, well, the same estimate that we had before. There's a slight change in this boundary domain, this y, right, where we have to impose our control. And so basically, y is just slightly bigger than what I had mentioned before for the multiplier estimate. Right, so y is any open subset of the boundary that contains this thing here that we had before. Okay, and then everything else, f0, t0 is as we defined. Okay, and so well, kind of this infinitesimal loss in our region y. This comes from the fact that we perturbed our f0s a little bit, right? And so this means that you're not going to pick up the exact region on the boundary, right? It'll be slightly perturbed, right? And that's where this slight loss comes from. And the fact that this loss can be arbitrarily small comes from the fact that our perturbation from f0 to f epsilon can be made arbitrarily small as well. And so that's the reasoning behind this. And then again, this improves upon the previous multiplier results by generalizing from free waves to general waves with lower order terms. And I already explained this discrepancy between this region y and what we had before. And again, if you compare it to the previous Carleman observability results for static domains, then this exactly improves upon what was done before by restricting the control region also to the null-cone exterior. Okay, and then finally, let me just mention in the actual final slide the related results and questions, right? And so the first one is a similar question of interior control, right? And so this is something that was recently done by my PhD student, Vebov Jenna. Right? So he's done the improved control for static domains, and then currently he's working on domains with moving boundaries with controls in a weaker space. And then point 2 here, I think, has already been mentioned, which is this question of geometric wave equations. Right? This control problem for wave equations on non-stationary Lorentzian settings. This is largely unexplored. This is currently a work in progress with my PhD student as well. And then lastly, the hope is to be able to apply these tools to study nonlinear wave equations, right, where one just cannot kind of assume any kind of analyticity. Okay, so I think I'm well over time, so let me just stop here and thank everyone for their attention.
Thank you. Are there any questions?
I have a kind of a naive question. Arick, maybe you mentioned that, but what can be said about the regularity of the optimal control?
Right. So I mean, so I guess this whole setup that we do here, right? It's done in very specific spaces.
Right.
And so for the on the control side, you're looking at solutions, I guess, in L2 cross H minus 1. It's very irregular solutions, and so there the natural regularity for the Dirichlet data to make the problem well posed is an L2, right? And so any control you get will be an L2, and the optimal control will be the one that minimizes the L2 norm.
Right. Okay. But just out of curiosity, so if you want to have a physical realization of the optimal control, so it's L2 is enough, or what do you have to? Is it possible to say?
I mean, I think for wave equations, it's a very difficult problem to kind of move beyond L2, right? Because that's the only granular spaces where you have well posedness. If you look at heat equations, I think they have there you can look at controls that optimize L infinity norms, right? And they have a very different interpretation. I mean, there are kind of I think people do look at problems where they only where they look at not just not just exact control, but also control with constraints, right? They can only look you can only take positive controls, for example. People look at these, right, and that perhaps gives a more physical flavor to optimal control to optimal controls. But I don't know of too many things of that sort being done for wave equations. I think most things I've seen are for heat equations.
And you know, for elliptic systems, like for differential forms, can one do control as well? I suppose you can.
As long as you're going forward in time, sure. Right? If you have you can certainly craft parabolic or hyperbolic systems out of these elliptic things, right? So and we can study those. I think that for heat equations, for heat type equations, they're a bit different in the sense that you can only do null control and not exact control because of smoothing. But other than that, yeah, absolutely.
Well, we're a bit over time, so let's thank Arick.
Thank you.
Thank you.